So let me start with this workshop of our statistical and complex systems group. And it's a pleasure to me to be here with you today. I'm going to talk to you about probing and controlling entanglement in quantum systems. This is something that came up like 2 years ago, and since that, me and some people, for example, Gustavo has been involved, also Josue, which is another student from the PhD. Yoshel is now doing some stuff also there. And we've been doing these things, different parts of these things together. So this is the agenda. This is what I'm talking to you about. Is first we will start revisiting quantum entanglement, which I assume that everybody is well aware of what this thing is. Then we will talk about just two important quantities to quantify entanglement, which is concurrence and the concurrence, which will be used in the main parts of this work we've been doing. Then I will show you some results that have been published in this. This is probing entanglement in continuous variable systems using a setup of 2 qubits and 2 oscillator system. Then I will tell you about some recent work regarding the modulation of the entanglement. One can do this kind of modulation when using this, more or less this same type of system. Some novel results is that actually for certain type of dissipation, you can more or less kind of keep the entanglement robust against this dissipation when modulating through the 2 oscillator system the entanglement in the system. And then by the end, I will tell you about a possible experimental setup that could be implemented in quantum computers, either IBM quantum computers and stuff like that. So quantum entanglement, the characterization of quantum entanglement is basically based on two things. One is the mathematical that we have constructed the quantum mechanics. So in this context, we can have states of composite quantum systems which are not factorizable, and that has strong consequences on it. Basically, is that one immediately fits the state of one of the systems of the composite system by measuring in any of the other complementary parts of the composite system. This is a direct consequence of not being capable of factorizing quantum states of the composite system. So one can say that the components cannot be described independently of the state of the whole system. So they are together binding. And the second thing, and possibly the most important, is the violation of the Bell inequality. So everything was kind of kept at the level of the mathematics, the framework of quantum mechanics, but it was until experimental confirmation, which earned the Nobel Prize 4 years ago, 3 years, something like that actually quantum mechanics really violate these Bell inequalities. So quantum mechanics cannot be described by sort of hidden local variables in the system. There should be some sort of non-locality there. But once this happens, everything explodes, right? So now quantum entanglement is real. It's been used in quantum computing and other algorithms that have been implemented in this quantum computer. So it's happening, right? Now, quantification. Well, it turned out that quantum entanglement was just not about some kind of spooky action or correlation, non-local correlations, space-time, non-local space correlations. But also, it turned out that there were a set of states that could be more entangled than others. So one needs to quantify this property. So from that, there have been before even confirmation of quantum entanglement experimentally, I think there have been a lot of measures that was derived in order to quantify this kind of thing. So in the literature, one can find any color and any taste of measurements for quantum entanglement. One of the most famous are concurrence, negativity, entropy of entanglement, and the eye concurrence. So before we start working on this, I was not aware of the eye concurrence, but I think it's not really used. I mean, people don't use it anymore because they are kind of constrained always to qubits kind of entanglement and stuff like that. So concurrence and negativity more or less do the job there. But when one start to ask about having entanglement in something which has not a discrete basis, that becomes much more complicated. For example, in the context of continuous basis systems, like field systems, Gaussian states, or CAD states, Fock states, stuff like that, right? Superpositions of Fock states. Now, these two important measures that I would like to talk to you first is the so famous concurrence. I think everybody's aware of this thing, and it changes. It has a very simple description if we are working with pure states, and it becomes a little bit more complicated whenever we go to mixed states. Now, the problem is that it becomes incredibly more complicated as the Hilbert space dimension increases. So it becomes a kind of problem of search and find stuff, right? Like finding minimums or stuff like that. So this becomes really difficult, and when we move out from discrete basis, for example. Now, the other important thing is the so-called the eye concurrence. Now, I have read that this eye concurrence is a generalization of the concurrence. I am not completely sure about that, but the important thing about eye concurrence is that it puts together the degree of mixture in the system to the degree of entanglement in the composite system. So this is some well-known stuff. Typically, we know that if we have a composite system which is pure and it can be entangled, if we do local measurements of one of the components, then we will see a mixture, a mixed state of this system. So this is basically the idea. The eye concurrence is giving us the amount of entanglement between the system A and B with regards to the purity that the system A or B has, right? If the whole system is a pure state, then the two purities are the same. If the whole system A and B is pure, then the purity of the individual systems, the way when you look at them locally, system A or system B, then you will see the same degree of mixture in the system A as in the system B. This is confirmed by the Schmidt decomposition. So any composite system which is pure can always be decomposed, for example, in this kind of orthogonal basis. And then if you want to trace out purities, you trace out B and then calculate in the reduced system A, you calculate the purity, then you get some amount, which is exactly the same for the other one, if you do the other case. So this is a cool thing because it's helpful to more or less track the entanglement in the system with this local one. So, for example, let's suppose that we have a system A and system B. They are composed systems, and there are some mechanism that makes entanglement in them. So, the eye concurrence will tell me that the more mixed the state A is, then the more entangled 2B is, and vice versa, because they share the same purities. Now, the one can ask one question: what if the system CAB, the composite system, is not pure. When one can think, but this is, although the first is correct, the if you know there is entanglement here, then locally they are mixed. The contrary is not absolutely true. If they are mixed, it doesn't mean that it is because you are looking at this one locally and it was entangled with something else, right? At least not so far confirmed. So if we have this guy which was not fully pure, then one could think that there's, because there's perhaps some entanglement or some interaction with an additional system which you are maybe not aware of it, and there's some sort of degree of entanglement with this C system, the whole composite system CABC will makes you suppose that everything is pure then, because you are including everything else that you wasn't considering first. Then now you have the chance to make everything pure. And then if you look locally to this system CAB, now you will see there's some degree of mixture here, and then you cannot anymore use the Smith decomposition to argue that the degree of mixtures of the more individual systems like A and B are the degree of mixture has to do with entanglement. So there are some techniques to calculate the Schmidt decomposition. I think it's called distillation or something like that. But for mixed states, or it's, I think we, at least in this work, we wanted to just keep at the level of pure states. Now, the question here, I think that I made this slide just to ask the question, perhaps for everybody, that what if just the way that we are looking at the world, like we are seeing mixed states, it's the way we measure stuff. But inherently, the degree of mixture in these things is because you're not considering the whole thing around. There was some degree of entanglement with the whole thing around. And by looking locally, you will only get access to the mixture of these states, not the whole scenario, right? And that could be quite interesting because basically classicality of everything comes out from the idea of mixed states. You have to get rid of quantum coherences and stuff like that. So it's perhaps everything could be basically entangled, but locally everything is classical, right? So now let me talk to you about this about probing entanglement in one specific setup. Now, before going there, let me tell you a little bit about the dephasing coupling model. This is a very important model because, one, it is analytically solvable, it is integrable. The second thing is that it can be really realized in experiments. So sometimes people call this kind of coupling like dispersive phase star regime or something like that. And it can be engineered either in quantum cavities with field and atoms there, like this standard used for quantum computation. It has a more direct implementation when we think about just at some junctions and superconducting oscillators to couple many of these devices coupled precisely in this way. And so experimentally, it's easy to get this thing. I mean, easy. I've never done it, but I suppose it's a mature technique, I would say. So what happened here? See, if we solve the system and we look to reduce dynamics of the qubit, we will get this kind of dynamics for the system. We will always have constant populations in the qubit, and these functions are called the coherence functions, not decoherence functions. Coherence functions, because they are only telling us how coherences they start. Suppose that we start with a pure state, and we have uh, certain amount of quantity here, a fixed quantity, which solves this thing to be pure. And then we will see oscillation in the coherence functions because the system gets mixed and then gets pure back again and gets mixed and gets pure back again. This is at the two level, this is at the qubit level system. Now, interesting, if we get the I concurrence, yes? No, yeah, sorry. This is a mistake here. There is more. No. No, it's not multiplying. The thing is that this function is a oscillatory function. So it is not something that just increases in time. It increases and then goes back. Actually, it's this one. This D here. Now, this is the reduced dynamics of the oscillator, of the field dynamics. Yeah. Suppose that we start with a ground state system. This is a Gaussian, and this is the Wigner functions of the field. We start with a ground state at the Gaussian at the middle. As system evolves, then we see this vector which increases, this y1. The Gaussian splits in two, which moves contrary one to the other, and then after one period of oscillation, then they match together, and then you recover the Gaussian state at the beginning, right? And this distance, the absolute value of this vector is actually this measure. So we see that this thing increases and then goes back. That's why you see this oscillatory kind of decaying amplitude stuff, but then you recover it back in the qubit dynamics. Now, interestingly, if we compute the I concurrence between the field and the two-level system here, or the oscillator and the two-level system, we can see that these functions are actually connected to the degree of entanglement that the two of them have. And it is more or less clear if we see it from here or from the reduced cubic dynamics. From the reduced cubic dynamics, it's clear that if we recover the purity of the system, then we are completely disentangled from the oscillator. The maximum mixture, which is when these functions takes the minimum value, is when you are most entangled with the atom. And it can be seen also from here. We see that the initial state of the oscillator, well, this is completely decoupled from the qubit system. At the moment of the maximum distance, when we have the maximum deformation in the oscillator, then these are the bind dynamics together, right? The qubit dynamics and the field dynamics, they are completely unfactorizable. This will be like the maximum entanglement you can have between both of them. But after the period of oscillation, then you recover back the initial separable state between the two qubit and the field. So this is interesting. This coherence function can be completely related to the degree of entanglement that one has between these two systems in the dephasing model. Now, one important thing I forgot to mention in the dephasing model is that the part of the interaction is this thing. We are coupled through sigma zeta of the atom to whatever the other thing is. In this case, it's an oscillator, but in principle, the reduced dynamics of any atom will have this same form independently if you have an oscillator coupled to, or you have whatever you want to, right? The idea is that you have constant populations, so you're not really getting any energy, let's say, from the interacting system, but you are only kind of have this sort of dephasing in the dynamics, in the coherences. Now, this is the model I wanted to show you. So we have here 4 panels, which depicts 4 different scenarios. First, we have 2 atoms, we have 2 oscillators, and each of the atoms interacts via dephasing to each one of the oscillators. These purple shades are telling you more or less about the entanglement that happens between each atom to the oscillator when doing this dephasing dynamics, right? But now the idea is, let's suppose that we prepare the 2-atom system in a Bell state, and then let the phasing dynamics to do its job and see what happens with the entanglement that was originally posed in this two level system. After this, we would like to also test what if we start with entangled with a certain degree of entanglement also on the oscillator. This is what this panel says. And the other case is what if we only have only entanglement between the oscillator and the atoms and the two-level system are not entangled at all. These dynamics are also solvable. This is an integrable system. And
sorry, a question.
Yeah.
Because
So cat was just to put something like
it's not the cat state, right?
it can be a cat state. Actually, you can think of, if you have continuous basis for the oscillators, any non-factorizable state between the two oscillators, it's an entangled state. Cat is one. That would be superposition cat in one oscillator, superposition cat in two, and then you entangle both. You can also have Fock states entangled. Let's say you start with number states which are not factorizable, Gaussian states which are not factorizable through the covariance matrix, for example, etc. So we will try all these kind of different possible configurations for entangled oscillator states. Now, if we prepare, let's focus first on this case. Let's prepare the two atom system, the two qubit system in a Bell state, and then let's look at the reduced dynamics of this system. We will have this kind of density matrix for the composite system. Again, it's pretty much have a very similar shape as in the case of the single. I mean, in the case that you have constant populations here, and these are functions that will oscillate more or less in the same way as we saw, as we described before. Now, if we compute the concurrence of the Bell state, the dynamics of the concurrence, or I would say the dynamics of entanglement in this kind of state, this has an X shape of state, of the density matrix has an X shape. So there are formulas for getting this thing, and this immediately one see that the concurrence of the Bell state is exactly the absolute value of this f function, right? This f function can be calculated analytically. It's not, there is no numerics here. Now, if we go, then since we have this density matrix of the reduced two qubit system, if we get the purity of this thing and then we compute the I concurrence, because we saw this I concurrence goes with the purity. So we get this thing, and then we get this identity. This is kind of an identity that you will get this kind of identity whenever you have a dephasing coupling between the qubits and the oscillators. This will happen always, regardless of the whatever you are coupled to. You could be coupled to an oscillator, to whatever you want. So we have this thing. What is this thing telling us? In this case, the I concurrence, recall that it is telling us how much the system of the two qubit system, it's becoming entangled with the two oscillator system. This is what the I concurrence is telling us. While the concurrence is only telling us about the entanglement appearing in the two qubit system. So this thing means that if this relation holds, the amount that you lose in concurrence should be kind of gained in the entanglement between the two qubit system and the two oscillator system. But one important question is, what should be the entanglement that is, what should be the relation between concurrence itself, the entanglement between the two qubit system, and how it depends on the entanglement that for each qubit you get to each of the oscillators, not the whole composite two oscillator system, but to each one of them. Now, let's, for answering this, let's think on a copy system of this configuration. 2 qubits and 2 oscillators, but now the 2 qubits, these are not entangles. This will be kind of this, more or less like in this configuration. Now, we don't have initial Bell state here, we just have it, a coherent superposition in both qubits, which are separable, right? This will be our copy system, and from that we can calculate the coherence functions of a reduced system for each qubit. So we will trace out for one qubit all the other degrees of freedom, and then get the coherence function for that qubit. In the other qubit, we trace out all the complementary degrees of freedom, and then get the coherence function for the other qubit. And then it's very interesting. It is very interesting that we find that the concurrence exactly fits the multiplication of the two coherence functions only if the oscillator system is separable. If the oscillator system has some degrees of entanglement or interaction between them, then this thing doesn't hold. And that immediately is telling us that you can come up with a setup in which you put one entangled configuration of the 2-qubit system, measure your concurrence with regards to the interaction with the 2 oscillator system. You go to your copy system, measure the coherence where these are not entangled, the 2 qubits, measure the coherence function of each qubit, and then if you multiply these coherence functions, and that gives you exactly the concurrence that you see in the first configuration, the first copy, then you can say that these oscillators are not entangled at all. But if they don't fit, then there should be some entanglement in the 2 oscillator system. So it is important, but I think this is the thing that I wanted to show you. So the entanglement that is initially placed in the 2-qubit system fulfills this relation. Is the entanglement between the qubit 1 and the oscillator 1, entanglement with the qubit 2 or the oscillator 2, and only if you have no entanglement in the 2 oscillator system. Now, here comes the figures. Okay, I have several initial configurations for the 2 oscillator system. We have separable Fock states, entangled Fock states, separable cut states, and entangled cut states. See? Now, the black curve here is the concurrence of the 2-qubit system when in the first copy you have this Bell state. The red curve is exactly this F is the multiplication of the 2 coherence functions in the other copy state. If you take a look to the difference between them, they are exactly 0. And if you move to an entangled configuration, then this doesn't fit. This blue curve and this black curve are placed here just to see kind of the symmetry relation between both of them. You see, when you don't have any entanglement, then this black curve is exactly the mirror curve from the blue curve, right? So, and this repeats also for separable cut states. You have no entanglement, you have exactly 0 for the difference. And as long as you put some entanglement in there, then you see that you don't fit. Now, this is for a regular oscillatory behavior. The ratio between the frequency of the 2 oscillators is rational, and in this case, we choose to be irrational, immeasurable. It's the golden rule, the golden ratio. No. Yeah, this square of 5 minus 1 over 2. Yeah. Yeah. Which is, I think, the most irrational stuff we have found. So now, let us change the perspective a little bit. So quantifying entanglement in the oscillator subsystem assumption. Let's think about, because one thing is that I can say, okay, these 2 oscillators are entangled because my concurrence doesn't fit to the product of the 2 coherence functions. but we would like to say how much entangled this is, right? So we would like to kind of come up with a way to quantify the amount of entanglement. Although this is very hard, and most if we are thinking on continuous variable systems, it's really hard. So, but we can think about this idea that we saw with the I concurrence and this kind of conservative relation we saw between the concurrence and the I concurrence. And let's think about this, or let's state this thing. The initial entanglement present in the two oscillator subsystem must be equal to the remaining entanglement stored in the oscillator subsystem plus the converted entanglement. So now we are kind of thinking about how entanglement is redistributed among the whole composite system, and see if we can pick up some stuff to kind of quantify entanglement in the two oscillator subsystem. And so let's think about this thing measures the initial entanglement in the two oscillator subsystem. This thing tells us about how entanglement is evolving in time, right? And this thing will tell us more or less like entanglement that goes between the qubits subsystem and the oscillator subsystems, and entanglement that could appear in the two qubit subsystem. Now this could have many specific forms, because so far here is very, very general. But if we think about this relation, considering that we are using a dephasing coupling model, we can more or less try to define a measure. I mean, taking it out from the previous equation we saw, from the two qubit perspective. Now let's think about that this thing here measures entanglement in the oscillator. This thing in here measures exactly the same that we saw with the I concurrence, is the entanglement with the two qubit system and the two oscillator system. And this should be some sort of initial entanglement stored in the two oscillator system, for example. If we take this thing, if we use this assumption, then we get for a measure of the entanglement in the two oscillator subsystem with something like this. Recall that since we have this two oscillator, two qubit system, the whole thing is pure. We can use the Schmidt decomposition and still change the purity of the two oscillator system to the purity of the two qubit system. That holds. And then we can more or less describe this quantity to check out if this fits with the entanglement stored in the oscillator. Now, but for checking this, we need an example that can be where entanglement in the two oscillator system can be measured. So we use this two-mode squeeze vacuum state. This is a very famous continuous variable entangled system, which is kind of a Gaussian system, which is covariant matrix, has non-diagonal terms connecting the different degrees of freedom of the two oscillator system. Yeah, not only in blocks, but outside the blocks. So you have this covariant matrix has elements there. So they are entangled squeeze. So it's kind of if one squeeze shrinks, maybe the other go something else, stuff like that. So they are entangled in this case. And the other thing is that this has a parameter of entanglement. So these elements of the covariant matrix depends on a parameter R, and as long as you actually I missed one figure. Yes. Give me a minute. Okay, I missed this figure. This is the same case as I showed you before when looking at the concurrence and the product of the two coherence function. For this exact model, the two vacuum squeeze state, when R is 0, we see that these two guys fits exactly. And then as we start to increase entanglement in the system, then we see how they start not to fit together. So this we did before. with the other case. Now, if we go now to this if we go now to this new measure, this C with a tilde above, that should be measuring entanglement in the two oscillator system and only relies on the purity of the two qubit composite system, this is what we get. The red one is our measure for entanglement in the two oscillator system. The black one is exactly this negativity measure for entanglement in these two squid mode state. And we see features that fit with one and another. So this is the important thing. We see for the, let's focus on the red one and the black one. We see these kind of features that are kept together, right? And which are not captured, for example, when measuring individual purities of the system. This, for example, this blue curve in here, this P here is a corresponding measure which instead of measuring the purity of the composite two qubit system, we measure the purity of one, the purity of the two, and then multiply them. We miss that features in this other quantity. So it's a, I mean, we cannot say that this is a really a good measure for saying about the two oscillator entanglement, but at least kept some features that a good measure will like the negativity will keep in this case. Here is also when we go irrational in the ratio between the frequencies, and then we start to see that if the dynamics are more complex, then we start to lose that good description. Okay, so this is half of the talk. If you are bored, please give me a couple 20 more minutes, and then I will finish. How am I on time?
10 minutes.
10 minutes, okay. Okay, now let's change the whole perspective. Let's think about the new scenario. Now, let's see that we are not focused on determining whether a continuous basis system like the two oscillators have entanglement. But rather, let's think that our purpose is that we put the two qubit system in a Bell state or any entangled kind of state, and we would like to manipulate stuff within the two oscillator dynamics such that we can kind of change the entanglement in the two qubit system. They are still coupled. This is exactly the same system as we saw before, the phasing coupling. But now we will include one additional term, which is an interaction between the two oscillators. And this is a linear interaction in the context that dynamical equations are linear. It's a linear system. So it's still solvable. That's my point. We could go with higher kind of, non-linear interactions, but then we will have to move to some numerical approximation of this. And if we are talking about continuous basis systems, that could become very complicated. So that's why we kept to the linear system. Now, one additional thing is that depending on the alpha and beta parameters, these two oscillator dynamics, they have a very rich dynamical regimes in the two oscillator system. So we need to go to study more or less the dynamical regimes of the two oscillator system when we change alpha and beta, which are the coupling parameters between the two oscillators. And everything in the dynamics of the two oscillator system is stored in this stability matrix of the system. This stability matrix is actually one of the key points when solving analytically the whole thing. And we have two oscillators. We have a 4x4 stability matrix. And exponentiation of this matrix gives us the dynamics of the two oscillator system. So what we would like to do is to study eigenvalues of this stability matrix. And the first thing we see is that the determinant of A has this form. So the system, the matrix becomes singular for values of alpha, beta, plus minus squared of omega. So this will give us kind of our thresholds between transitions from one stable to non-stable or unstable dynamics in the two oscillator system.
What is omega? Sorry.
Omega is the ratio between the frequency of the two oscillators. So these are the real and imaginary parts of the four eigenvalues we have for this stability matrix. We see several regions here. We see here is a 0, 0, so this is exactly back when what we have at the beginning. These curves we saw, they are at this point P0. Now we have a region of stability, this hole inside the P0, because all the eigenvalues are complex in this case, right? So we'll always be seeing oscillatory behavior on this regime. But then we have regimes like are, for example, mostly real. We have regimes which are only oscillatory also, but beyond this region, these two parts from here. These are only imaginary elements of the eigenvalues. And then we have also regions of mixed eigenvalues, complex eigenvalues. So we have some of them which are only imaginary part and some of them which are only real part, right? So they will give us a different form of the dynamics. So let's see. Black curves are the typical we saw in the two-qubit system when there is no interaction between the oscillators. These are the black curves here. Now, if we start to move, for example, in region P1, A or B, these are when we have only real eigenvalues, and then we see a rapidly decaying behavior of the concurrence. Interestingly, if we go to the only imaginary eigenvalues, which will be P2, for example, in the case P2B, which is the negative part of the eigenvalues, we see that oscillations are much more recovering in amplitude than when we don't have interaction between the oscillators. So it's like if we put our system when the two oscillators do not interact, then we see a feature of the concurrence. But if we put them to interact, we can enhance concurrence in the two-qubit system in that specific regime, right? We also see some transitions, for example, from oscillatory regime to a decaying regime, depending on the value of the omega. And these are typically this is what happened in the P2 regions, the regions that have real eigenvalues and imaginary eigenvalues along. So this result is interesting, right? So we can kind of, even though you are coupled to the two oscillator system, the coupling to a two oscillator system, if you put them to interact within this specific regime, then it's kind of you more or less like a decouple or from the two oscillator system. So typically, what one will say is that the entanglement cannot flow absolutely to a two oscillator system because the two oscillator system is too busy doing correlations among itself. So it doesn't flow to that point. See? So that's an interesting question. That's interesting result. Now, from what we see, we saw that there are decaying regimes and there are oscillatory regimes, and this is only by tuning the coupling parameters between the two oscillators. So we can think of tuning these things from going to Markovian to non-Markovian regimes in the entanglement dynamics of the two qubit, for example. Suppose that we start here. So here in this figure, I put you these transition thresholds, which are the dotted lines, the dashed lines. And blue stuff are oscillatory regimes in the concurrence. Pink stuff are decaying regimes. And these things tells you about transitions. This depends on omega, and it could be either oscillatory or decaying regime. So, but in this figure, for here, we are seeing the concurrence of the two-qubit system. We start here, and that's the moving parameters from alpha to move to this part in here, and then go back to an oscillatory regime above here. So we start with the blue continuous line below this one here. And then we start going downwards as we move to this decaying regime until we get, you see here's a little green peak because we are at the verge, at the limit of this regime. And then we move to the other one And then we have completely Markovian dynamics. So entanglement flow to the two oscillator system, and it got lost there because the configuration space was so big that entanglement went there and never came back to the two oscillator system. But then suppose that we start moving now beta parameter and start going back to oscillatory regime, and then this is the square market figures, and then we start to recover again the non-Markovian dynamics. Non-Markovian in the context that we see entanglement flowing out from two-qubit system and coming back to the two-qubit system. That's why we see this recovering in the concurrence. Now, what happens if we put dissipation? I'm particularly interested in the dissipation because we saw that for certain dynamical regimes of the two oscillator, we can more or less insulate the concurrence in the two-qubit system, the entanglement in the two-qubit system. We ideally will have two scenarios. One is when we put local dissipation in each of the oscillators, and the other one is when we put global dissipation in the two oscillator system. Just to let you know, I haven't finished this thing because that's a lot of math there, but these guys are more or less straightforward. So we studied these ones, this local dissipation. Now there's a problem. If interaction between the two oscillators is strong, which is basically what we want because we want to go outside the traditional dynamical regimes, then probably local dissipation is not going to give you the real scenario. Perhaps approximated, but not the real scenario. One will have to go to some sort of global dissipation regime. Now we will start to work with master equations. The local dissipation will go with two dissipators, each for one oscillator, having Lindblad form. And the global dissipation will also go to a Lindblad form, but now instead of having this creation annihilation oscillator operators for each oscillators, we have a global creation annihilation operator. So that mixes everything, and it's become really complicated. I mean, it's not complicated, but it's a lot of quantitas. So this is the important thing. Black fat curve is no interaction between oscillators, just dissipation. And these are concurrences. And we see concurrence have this profile. For these two dynamical regimes, this is one of them. We saw the recovery in the amplitude of the coherences. We see a really much more above rate of much less rate of decoherence or dissipation than when you have no interaction between the oscillators. So perhaps it is possible to kind of manipulate parameters of coupling between the two oscillators to kind of protect entanglement in the two-qubit system. Yeah, this is for G0.1 and this is for G0.5. This is the interaction between oscillators and qubits. So this is quite interesting. And okay, now just to finish, now just 2 minutes more. Now, what would be interesting is to see if some of these results are true. And for that, one would like to kind of implement some of these things in a quantum computer, because besides whatever people say, seems to me that quantum computation is only working for if one has the idea for how to put down an experiment of quantum experiment into this kind of circuit gate operative logic, then you don't really need to buy a big laboratory and do quantum mechanics, right? So I think this is one of the most useful things that quantum computers can bring us besides whatever the people is saying of commercial stuff and that thing. But anyways, so now the idea here is that instead of using two oscillators, we are not distancing, improving entanglement in continuous basis system. What we are interested in see if this thing holds, and if it holds in the two oscillator system, it should also hold if we move from two-qubit two oscillator to two-qubit two-qubit system. And we tried with two types of coupling. The phasing is always there, sigma zetas, But then we can take sigma zetas in one of these things or sigma x in the other exemplification. Now the first thing we want to see if this thing holds for these two systems, and yes it does. So one of these curves is the concurrence and the other one is the product of the two fidelity amplitudes whenever these two other qubits are not entangled, and if they become entangled then they don't match exactly. So there is a difference, right? Exactly the same results we saw before. But what would be the idea? The first what we would like to try is the sigma zeta sigma zeta, because this one is simple. And for example, unitary evolution of the whole composite system will have these forms. Is everything here commutes with each other, so we can split this thing into separate unitary stuff, and then these things actually they look like rotations. Now this will be a double rotation for the interaction there, but there are some quantum platforms that can handle double rotation, so it's realizable. So the idea should be then to prepare the states in 2 qubits Bell state and 2 qubits not Bell state, and we can get kind of this initial state configuration, but doing this set of gate. I mean, by applying this gate, and then eventually the dynamics of the system will be then therefore to apply these rotations with different angles. Different angles will mean time evolution, right? So you use first small angle, so that will be the first time step. Then you repeat the thing with a double of it, and then you go double time step, and then you do the whole thing. Then you have the whole dynamics, and then you will have to do full tomography on the 2 reduced qubit system for getting the quantities that you want, right? So you get these observables, and then you can get that full tomography of the 2 qubit system that you're interested. And this will give you this will bring you the single coherence functions by recovering single states of the qubits. And then you can try to check all the stuff that we've done with having reconstructed the full things in the system. And well, that's what I wanted to tell you about. So as a summary, we have introduced a protocol for indirect measurement of continuous basis system entanglement. We have explored the dynamics of entanglement in 2 subsystems coupled to 2 oscillators. It be modulated by controlling interaction between oscillators. We have discussed the effects of local dissipation, and for some dynamical regimes, we saw this is by tuning the coupling parameters, we can protect the entanglement in the 2 oscillator. And then we have proposed a possible experimental confirmation setup in the quantum computer machine. And that's it.
Question.
Comment. Can you go back to the 2 qubit case? To the Hamiltonian that you have there?
2 qubit, 2 qubit?
Yes, you have. Yeah, this one.
Zeta model?
Yeah. So you're saying that you want to implement this in separate, and this is only 2 qubits, right?
4 qubit.
4 qubits.
4 qubits. So you have.
No, but they are separated, right? You have 1 with 2 and 3 with 4, and they do not mix.
Okay, the idea is you will prepare 1 and 3 in a Bell state, and then 1 will interact with 2, and 3 will interact with 4.
So you have only 2 qubit interactions.
Yes,
So
but the other 2, let's say it's entangled already with the other one. You see?
So
yeah,
you might be interested. Hera has a package to decompose 2 qubit matrices, entangled 2 qubit matrices, and they give you in CNOTs and programmable gates.
Oh, really?
Yes.
Okay.
You give a 4x4 matrix, and then it gives you back the code.
Okay.
For Qiskit.
Rochelle? We need to talk to Adrian. Okay. Thanks.
Another question, comment? Okay. I'm not sure if because it's more philosophical.
Yeah.
No, but I think it's might be important. There are people who say, because we're talking about oscillators, so you can see you have a particle on a finite lattice, right?
Uh-huh.
And it's a single particle. You can put it into a cat state. That's why I was interested. So that caught my attention, the cat. So that means that this particle can either be in one side or in another side.
No. I mean,
This
there
would be a
are
cat
two
state.
possible idealization of a cat state. You have a single particle,
Yeah.
and then you have a superposition of coherent states
For a single,
for the single
okay.
particle, and that's a cat state of the
Yes.
single particle.
Yes. No,
Then
I
you can
understand.
have-
Yeah.
Yeah. Okay.
Because then you're talking about the entanglement of two cat states.
Yes.
That's true entanglement.
Yes. That's my
I
entanglement in
understand.
the two oscillators.
But you can also go, that's what people do a lot, you can go into the second quantization picture, right, and say, okay, in each side I can have excitations or not. And then suddenly the cat state becomes an entangled state in this picture. Entanglement of excitations. Right? And is there an experimental way, or maybe how to say, conceptual way to distinguish cat states from entangled states? In the sense of, say, in terms of this Bell measurement. I mean, I think the point is that you have your second quantization picture, that's fine.
You are thinking about a field which
But you go-
pops out
Yeah,
vertical or
Yes,
excitation.
well, in principle, they go to that model, but at the end they say, but we conserve excitation number, right? So we only have one excitation, but still, if you calculate the density matrix in this basis, you get the density matrix of a Bell state.
Now, I think
But
it could be
experimentally, how would you
it could be a
test?
matter of interpretation, because suppose I'm thinking that I'm guessing that you're talking about the field. So what's the field should be think about one single thing or a composite thing of many stuff. That's the idea. Because if we think of it as a composite stuff of independent thing, then for sure this is entanglement, right? But if these are manifestations of a single thing which are basically expanded or non-local or something like that, but it's a single thing itself, then it's just one. There's no composite system there. It's one single.
Maybe, suppose you have a photon,
Uh-huh.
and you go to this picture, right? It's a single photon, and it might be in two places.
Yes.
Can you do Bell violation experiment? You can't, right? I think because you have to calculate correlations between four states somehow. I don't remember, but and that's not. Well, this is a kind of question, not about interpretation, but about, say, experimentally nail down. This is a Bell, a true Bell state, Bell state, or if it is just a cat state. I think maybe it's more common. Can discuss this.
Yes.
Okay.
Okay, if there are more questions, then I thank you for your assistance and your attention. And please stay around for the next talks. See you around.